In this video, I want to go over how you could implement hybrid search with KDB.AI. The first thing we're going to do is install KDB.AI client, settings transformers to generate our embeddings, and LangChain to actually process our unstructured data and chunk it. Let's also download our data, which is just a speech made by the Federal Reserve Chairman about inflation. And let's also import some packages. And now let's use LangChain to load and chunk our data. So we will use the LangChain text loader to load it, the LangChain recursive character text splitter to split our data into chunks of around 500 characters. And then let's use the split documents function to get a list of all the chunks created and store that in pages. Next, let's look at the first page. So let's just look at these chunks. What we see is that they're just strings. They're just strings of around 500 characters. Now we could create a blank data frame to store our chunks and vectors that we're about to insert. To generate our sparse and dense vectors, we're going to use a tokenizer and an embedding model. To generate our sparse vectors, we're going to use BERT tokenizer fast to generate tokens using the BERT based on case model. And our embedding model is going to be all mini LMv6 in this case. So let's instantiate both of these. And then we could use our tokenizer to tokenize a query. Now to show an example, I have this query here and I repeated it twice to just get a better understanding of how tokenization works. And as you can see, it broke it up into different tokens. We could also get the numerical representations of these tokens. So if I use this token function here, I get the numerical representations of these tokens. So here we get repeating tokens because we have a repeating query. But we also have these additional tokens, 101 at the start and 102 at the end. And BERT uses this to signify the start and end of a sequence. So when we process our query and the documents that we're trying to insert into our vector database, we want to remove these tokens so they don't have an impact on our search. They're just not relevant. Now, for every single chunk, we want to generate a dense vector and we want to generate a sparse vector. Our dense vector is generated using our embedding model, but our sparse vector uses this token function to create a mapping from every single numerical representation of a token that we see to the number of times that we see it. And this additional code here is just to remove the special tokens that indicate the start and end of a sequence. Now let's add that to our data frame. And we see our data frame here. Our data frame has an ID, it has a chunk, it has a dense vector, and it has a sparse vector, where a sparse vector is a mapping between tokens and the number of times that we see that token in every single chunk. We are ready to insert this data into our vector database. I already have my environmental variable set, so I can instantiate a KDB.AI session. So here my session is instantiated, and let's define a schema. Our schema is going to have an ID column, a chunk column, and a dense column to store our vector embeddings. It's going to use a flat index, an L2 similarity metric, and it's going to have 384 dimensions. But it's also going to have an additional column to store our sparse embeddings, or sparse vectors. And this additional column has the hyperparameters of K and B. we're setting the defaults when we create the schema, so we don't have to pass them at query time or at inference time. But this is something that we can change at inference time. Now, it's not very often that you need to do this, but this is something that you can do. So let's define our schema right here. And next, let's drop the inflation table if it exists and create a table called inflation with our schema. Once we've created our table with this schema, let's insert our data that is stored in a data frame into our table. And next, we can actually query our database. We have this query, in this case, it's 12-month basis. And this is a query that makes sense both semantically and from a keyword perspective. Then let's create a dense query. We're using an embedding model to create a dense query. And let's also create a sparse query. We're doing the same thing we did for our documents to create a sparse query. And then let's just make sure that we can see the full output. And I'm ready to search my database. So the first thing I'm going to do is search with my dense query. Our dense query doesn't really care about keywords, so we don't really see this 12-month basis keyword. But we should still get relevant results. Next, let's search with our sparse query. This really cares about our keywords. So our specific query should show up. And that's exactly what we see here. We have this 12-month basis, keywords, or set of keywords, show up first. And if we look closely at the next results, it shows up there as well. We could also do a hybrid search. And in this case, we're passing our dense query, our sparse query, which is our sparse vectors. And the default alpha parameter is 0.5. So we're going to re-rank the results with the 0.5 alpha parameter. And this is basically making two searches. It's making a dense search, and it's making a sparse search, and it's re-ranking. And what we get is a result that isn't theoretically the best of both worlds. We're getting results that are relevant in terms of keywords, and they're relevant in terms of semantic meaning. It's very difficult to tell in this particular example whether the results are better or worse, but bear with me here. We can also pass an alpha parameter. An alpha of 0.1 or closer to 0 signifies a strong sparse bias, which means that our keywords are going to have a much greater impact on our ordering than the semantic meaning. So let's search with a strong sparse bias and a low alpha parameter. And what we see is that we still get 12-month basis in our first result. We could also search with a dense bias. Now this does give a small boost to the exact keyword match, but it mostly focuses on semantic meaning because our alpha parameter is 0.9. And this 12-month basis set of keywords no longer appears first in our results. When we're doing hybrid search, there are also the additional hyperparameters B and K. B signifies the document length, impact, and relevance. If our document covers many different topics, we want B to be high. Otherwise, we want B to be low. In this case, our document is just a transcript of the Federal Reserve Chairman talking about inflation, so it makes sense for the B to be low. K signifies term saturation. Basically, at what point does seeing an additional instance of a certain keyword stop giving that document an additional boost? In this case, term saturation isn't too important. I guess it makes sense that for our particular chunks, if we see a particular keyword many, many times, it's probably more relevant than a document that has it a few times. So we can make term saturation high in this case. So let's make a query with a low B and a high K. And we get this result. So it's hard to tell whether this result is any more relevant, but it makes sense to set this particular B and K for this particular query. In general, I wouldn't worry about the B and K hyperparameters just because the alpha parameter is much more important and there are other parts of our search pipeline that are much easier to optimize. Another thing to note is that when we're making a hybrid search, we're making a sparse search and we're making a dense search. Now, when we're re-ranking with alpha, often we get results where if something is extremely relevant in terms of keywords, it might not be in first place, for example. Or if it's extremely relevant semantically, it might not be first just because it might have a low score in the opposite category. And one way to account for that is to use re-ranking. So a re-ranking model will have a better understanding of both keywords and semantic meaning. So it'll be able to take your sparse results and your dense results and often re-rank in a much more effective way than just using the alpha parameter. But using the alpha parameter is instantaneous and usually gives you better results in terms of recall out of the box compared to just using sparse search or using dense search. Another thing to note is that when you're introducing a search system to a user, they might want to just use keyword search, even if you have a dense or hybrid search retrieval system. So that is just something to keep in mind. They might want keyword search, they might want dense search, they might want hybrid search. Just because a system has better accuracy or recall overall doesn't mean that it's the best search method for the user. And that's it. We are ready to drop our table to conserve resources. And I really hope this video was helpful in understanding how to implement hybrid search. And I'll see you in the next one.